Hello everyone. The purpose of this video is to explain the solution for the midterm extra questions. The ones related with inverse kinematics. Okay, so the questions were something like this. So this is one of the questions. The length of L1 is 2.2. The length of L2 is 3.8. The origin of the kinematic change is at 2, 0, 0. And we were asking if we place the end effector at coordinates 8, 0, 0. And using an up vector, what was the transformation for L2, I guess. So the thing is, these questions were intentionally designed for you to imagine this system. I know that sometimes it's a bit complicated, but even the way we graded, it was, depending on how was basically you were observing this, geometrically speaking. Okay, so I will make a quick demo here in 3 to the max to show you what is basically the interpretation of this. I'm pretty sure most of you already know the solution, or in the end, you had probably the correct intuition, but just I just needed to do the video. I think there are still people that might be struggling with this. So I will create two objects for L1 and L2, and I will give them basically the same height as the length that is basically referred to the question. So I have two boxes. One is called L1. I can even change the color. So this one will be blue, and it has 2.2 units, which is basically the length for L1. And the other one, it's called L2, and it has 3.8 units, which is basically the length of L2, right? I will also check, maybe change the color to whatever, green. And so we have these two guys here, right? The position of the L2, I can, if I want, I can maybe put these guys on 0, 0, 0, right? And the other on 0, 0 on X, and maybe in 2.2 on Z. But that is not strictly necessary right now. It's just, I can. This is basically the way to the better way to imagine this as a kinematic chain, because obviously this thing needs to be connected, right? A kinematic change, we mean basically links that are connected, right? Like a robotic arm, right? So unless my code will, in the end, modify the position or define the correct position of this guy, I will just visualize for now these guys as if they were connected. Okay, good. So the thing is, I think the first confusing thing was probably that I designed the question based on the video, right? So in the video, the demo was I was using 3 to the max, and 3 to the max has the vertical axis. The vertical axis in 3 to the max is the Z axis, right? So I think a couple of people were confused, because we were also using other examples in the lectures or even in the midterm, in which the vertical axis of the kinematic change was actually the y-axis, or maybe you were thinking that it was the y-axis. So the thing is, that is something that happens all the time in computer graphics. I told you already that we sometimes need to keep switching between y and z as vertical axis, and we kind of make those mistakes. I take that mistake. I think that was my fault. I should have specified in the wording of the question that my intention was to have a kinematic change, right, whose vertical axis was the z, right? But in the end, the way we grade the questions, we were also allowing people to think that it was y. Okay, so in the end, we were basically also having different versions or different correct versions, either if you were using the z-axis as the vertical one or the y-axis as vertical one. But sorry, I made that mistake of not exactly telling you what was the vertical axis. So again, I designed the question based on the video. The video I'm using 3 to the max. X, Y, Z is the floor. Sorry, X, Y is the floor, and Z is the vertical axis, right? So this is what we have here, right? So if I select the objects, we can see this is X, Y, Z, red, green, and blue. This is the way we usually color the axis, right? So the question says that we have an end effector, obviously, at 800. Okay, so I will create another object. Helpers point. So this will be my end effector. And this guy, for now, I will put it on top of my kinematic chain. Okay, for now. Because what I want is to basically to create an animation in which the end effector is basically like touching the point of the kinematic chain, and then like moving right on space until it gets to its right location, and so we can see what is going on there and how basically the axes are rotated and things like that, right? I think in this question in particular, yes, the origin is not at 0, so I will just move this. The origin is obviously the position of L1, right? So I will move L1 and obviously everything else to be at 200. Okay, so this is basically what we needed to imagine, right? We have a kinematic chain, right? Basically two links that are connected or mechanically connected, and the origin of L1 is 200. We can see it here, and the length is 2.2 for L1, and the length is 3.8 for L2, right? So I will take my code. So this is my code, right? This is almost the same as the one I did on the video, right? So I'm defining L1 and L2, I'm defining an end effector, I'm just getting the objects from the scene. And I have two functions, right? So circle, circle. I don't know why I have these two here, sorry. Yeah, I don't know. So I have circle, circle, intersection, right? Basically using the triangles theorem to compute the circle, circle, intersection in the specific plane. So we need to get the origin, we need to get length 1, length 2, the position of end effector, and the up vector, right? And that's it. We compute, I mean, I'm already explained this thing, the part of the of this algorithm. And if you remember, what we were doing is basically to compute the intersection between those circles, and using that intersection as a target, right? We were, in the case of L1, we need to compute its transformation matrix, right? At least it's the rotation part of its transformation matrix by constructing three vectors, W, U, V, and W, right? And the first one we compute is basically the one that it will represent its vertical axis, which in this case in particular is the Z axis, right? Because this is how this is done in 3 to the max. And that is my lookat vector, right? So this is the lookat transformation, which is basically takes the position of the object, the position of the target, and the up vector, and creates this cross product things to compute the new vectors, right? So the first vector is obviously the one from the lookat vector, this one, which is basically the normalized vector, that is the target position minus the object's position, right? The object's position is obviously the origin, in the case of L1, the origin of this guy, right? And I made a mistake, maybe, I mean, if you haven't heard about that, I was doing that that code as live coding, and I basically flipped a couple of cross products, and somebody noticed that, right? The way it is, the way it's done here, this is exactly as the video, right? So the problem of the order of these cross products is that we are not complying with the right hand rule, right? So basically what is happening here is one of the axes is basically flipped. I'm kind of like making like a mirror on one of the axes. The thing is, it was not evident at the moment I was doing the video because we are basically just using boxes, right? And yeah, but if you like look closer, as some students look closer, yeah, obviously there's a mistake, right? So I think Ivo was answering that post. So Ivo explained the post on Piazza, and yeah, and I think I also mentioned that on one of the lectures. So yeah, there is a bug in that video, right? Which is here, right? So the bug is this one, that I'm taking the cross product between the lookout vector and the up vector. So this should be flipped. And also these two guys should be flipped. These again, but again, these are the type of bugs that are very common in these things. It's usually very hard to spot these problems, because in this case it's just unnoticeable, right? I mean, the thing is not crashing and is working perfectly. And because you're literally flipping a box on one of the axes, you just don't realize that. So I think someone was like kind of like doing this manually, right? Kind of like understanding which was the direction of the axis. And what happens here is that once the matrix is already done, if you take the cross product between x and y, you will realize that now your thumb is not pointing to the z axis but to the opposite side. So this is wrong, okay? But let me show you what is happening and why is that a problem. So I will very quickly, yeah, I will make basically some cylinders that will represent the axis, the local axis of L1, right? The thing is, I want you to observe how these things are basically like rotating, right? Basically, these cylinders will represent U, V, and W from our rotation transformation matrix that is basically computed at this function lookat transformation. So again, I've created these cylinders right here. So red, green, and blue, they're kind of representing the X, Y, Z axis, or in this case, U, V, right? I've changed the names, U, V, and W. So these cylinders are basically just pointing on the directions of this U, V, and W axes that are basically the orthogonal axis from our rotation matrix, right? And I mean, I will just very quickly change the color of my links, because now, yeah, I had like L1 was also blue, so yeah, so now these guys are like pink and yes, and purple. Okay, so and then I need to do something here, because these guys, when L1 will move, these guys need to also move and rotate. So I will not code this part. I will just, I mean, this is very easy to do in Trees to the Max. I will just get these guys except for this L1, and I will just use this link to basically say that these guys, their parent is now L1. So now these cylinders are their parent is L1. So if you move L1 or rotate L1, they will kind of like stick together, right? What is happening here, right? You already know, is that basically the transformation matrix of these guys will be multiplied by the transformation from its parent, which is L1. Okay, good. So once I have this, now I will animate the end effector, right? So it says, the problem says if we place the end effector at the coordinates 8, 0, 0. So I will make this quick animation from 0 to 100, and I will put this guy at 0, 0, 8. No, 0, 0, no, sorry, 8, 0, 0. 8, 0, 0. There, right? So we have an animation from the end effector. So now, again, if I get my code back, I'm still using the wrong version, right? Remember, this is the wrong version in which I flipped, right? I flipped the order of the cross products. But yeah, but I can basically get the animation done, and this is what we have, right? And then, so we can see here, yeah, so we can see here that this is how the axes are aligned with that, with my error, right? So basically this is X and Y, or U and V, right? So if you take the cross product between X and Y, if you imagine that you're doing that with your right hand, your thumb will basically pointing to the other side, and it needs to point to the Z direction, right? Yeah, just a very easy mistake, to something that is very, very easy to happen. Again, it's not a big deal because in the end it's just like a flipping, right? But again, we took that into account. So when we were grading your answers on the midterm extra, we were also checking that, right? We were also checking if people were literally following the video, or if people were following Ivo's explanation that the video was having a mistake. Yeah, so either options were actually good, and we were giving full marks for every solution, right? It doesn't matter if you had this flipping thing. So if I get the code again and we make this correction, so this guy should be here, right? And this guy should be here. So if I run the code again, yeah, now you will see that if you take the cross product between X and Y, right, now you will get the Z value, which is correct. This is basically complying with the right hand tool, right? In the other case, what I was basically doing, I was converting the entire transformation matrix into a left-handed kind of. Yeah, okay, so this is correct. So now let's see what happens with the actual transformation, and yeah, but first let me show you something, because this is also something important that you need to notice. Please notice what happens when this thing starts to get animated, right? There's a flip, right? This is also something that could happen. This flip is not a problem of the code in this case in particular. It's just the way we are computing the vectors, right? Because we are using an up vector, and we are using the basically the up vector, and every time the up vector is basically like changing one side with respect to, in this case, the x, right? The x value, the x is basically flipped, right? It makes sense, right? We know that already, right? Depends on the order in which you are basically computing the cross products. It will be on one side or the other side. This was one of the most important things that you needed to notice when implementing the bonus question, right? This was some of these tiny details that we didn't want to explain, because it was, our intention for you, it was to discover this type of problems and basically solve this problem. I will teach you how to solve it once I get into the multi-joined inverse kinematic, right? So let's see. We have something like this, right? So what happens here, and this was basically happened with all questions on the midterm extra, is that the end effector is at the maximum distance from this kinematic chain, right? So seeing the numbers, right? The L1 plus L2, right, is basically 6 units, right? And because the origin of the kinematic is at 2 and the end effector is at 8, yeah, basically this length is 6 units, which is basically the maximum extension. So that was the key observation to quickly solve this problem. So the thing is, this question in particular, you didn't even need to compute anything, right? You could solve it just by imagining what was happening and observing that the end effector was basically at the maximum distance. So basically everything is like a straight line, and it was obviously aligned with one of the axes, right? So what is happening here, if I now put the same cylinders but now in L2, right? I just copy these cylinders, and now I have this axis or this visualization also for L2, and we can see the animation, right? We can see how this is happening, right? Again, remember what we are visualizing here, these cylinders here, they represent the column vectors for the rotation matrix, right? So because everything is a straight line and the end effector is aligned with one of the world axes, the question was only to imagine, right, for you to imagine the original axis from this links, right? It's local x, y, and z axis, right? The vertical x, y, and z axis, where they are pointing now, right? So the first column, right, is this one, is the local x. So now the first column is basically pointing to the y direction, right? The second column, which is this one, is pointing to the z direction, and the last column is pointing to this direction right here, which is x value, right? So, and obviously those, they need to be unitary, right? A couple of people were constructing these columns with numbers that they were bigger than 1. That is obviously wrong, right? Because we're not scaling anything, right? It's just rotation, so it needs to be only ones and zeros. So it was only to think where to put those ones and zeros, and basically where this straight line is pointing, right? And again, because we know that you might be confused, right, on these things about the axis, and you could also make mistakes at the time of the midterm. We were actually at the moment of the grading, we were actually checking the vertical axis, right? So basically, if in your solution your transformation matrix was implying that your vertical axis, or the entire straight line from your kinematic chain, was basically pointing to the right direction depending on the position of the end effector, it was almost not a big deal if the other axes were, I don't know, imagine that this guy is flipped or this guy is also flipped, but you had like kind of like 90 degrees rotation, things like that. It was not a problem in terms of grading. You were getting full marks. So this, in this case in particular, this will be the solution, right? So the transformation part, which basically the first three columns, right, will be this, right? So again, this was the original local x-axis, which is column 1. So now it's basically pointing to the y direction. Now this guy is pointing to z direction. This guy is pointing to x direction. Again, the way it is, these things are defined in 3 to the max, is that you don't need to give the fourth value from these affine matrices. So you only need to construct, so basically 3 to the max will automatically deal with the fourth column and the fourth row. But that also was not a problem in terms of grading your answers, right? Some people were giving the answers with only 3 numbers. Some people were giving with 4 numbers. So yeah, if you want to give 4 numbers, you will basically need to add a 0 for the first 3 columns, because these are the ones for rotation. And for the fourth column, you need to add a number 1. Some people were probably struggling with that because the syntax example we had, the fourth column on the example was 0, 0, 0, right? But you need to know that, I mean, we expect you to remember that column 4 is basically your transformation, right? And if it's the transformation, you need a 1 at the end. So the fourth column, the thing is, this is also kind of tricky, because the way we solve the inverse kinematic problem on the video, right, at least with this technique of solving inverse kinematics, is by computing, again, right, the transformation matrix for these links, right? But it's basically computing a transformation matrix that is in world coordinates, right? So despite the fact that this is representing a system that is a mechanic system that implies that L2 is basically connected to L1, right? The way we are actually computing everything is in local coordinates, right, for everyone, in world coordinates, right? Or basically, yeah, like the local axis, but in world coordinates, right? So we were not assuming that we have a hierarchy of transformations and that we were basically multiplying its previous matrix, right? So if you were solving these questions exactly as the video, this should be the answer, right? Column 1, column 2, and column 3 are basically the rotation part, and column 4 is the transformation part. And because it's in world coordinates, literally these numbers right here are, they need to be the local, not local, sorry, the position of this guy with respect to the world, right? So if I select this object right here, I can see that is 4.200, right? So you, again, this is just by you imagining or taking these numbers, because everything was aligned with one axis. It was very easy to get these numbers, right? And again, some people were confused about this, right? But there's a catch, because there's another way to basically respond to this question that is also correct, and some people got it correct actually. There's another way to see this solution as a hierarchy, right? So if you think about it, if you think this as a hierarchy, let me just, I will probably hide these guys, give me a second. Yes, so you think it as a hierarchy, right? And you say, okay, these columns 1, 2, 3, and 4 are basically the new transformation metrics for L2. But if you were thinking that L2 has a parent which is L1, and you're basically computing not a transformation matrix in world coordinates, but a transformation matrix in local coordinates with respect to its parent, it means that because everything is a straight line, right? It means that there is no rotation from L2 with respect to L1, right? It means that L1 is the one that is rotating, but in the end, you don't need to rotate L1. Meaning that, so again, this is a valid answer, right? So another valid answer will be to have an identity matrix on the rotation part, right? And that's perfectly fine, and it was correct. A lot of people gave that. A lot of people observed that if this thing was with respect to its parent, everything is a straight line, so there is no rotation in L2 with respect to 1. So a lot of people actually gave us this, column 1 and column 2 and column 3, an identity matrix for rotation, right? Because again, the thing is, there is no difference between rotation, right, from L2 with respect to its parent, which is L1, meaning that this should be the rotation if it's local coordinates with respect to its parent. But now column 4 needs to change, right? Because there is a difference in position from L2 with respect to its parent. Because its parent, the local coordinates from its parents are these right here, right? We can see the arrows here. So basically this object L2, right, is its position has a difference, right? If its local coordinates were 0, 0, 0, this guy should be here, because that is the 0, 0, 0 of its parent. But it's not. This guy needs to be on the tip of the parent, this axis, right, is not the x value from the world. So for example, right now, it seems that is the x value from the world, right? But it's not. This is not in world coordinates or view coordinates. It needs to be in the local coordinates. So in local coordinates, right, it needs to be set. If I get this guy, for example, and I ask to see the parent, sorry, the local also, it is also in the set coordinates, right? So it means that if you were, where is it? Yeah. So it means that if you were giving us the identity matrix for rotation part, because you were thinking that this is a hierarchy, right? And you were basically giving us the identity with no rotation whatsoever, it means that this guy should be 0, and this guy should be this guy should be 2.2, right? Because 2.2 is basically the length of L1, right? So this should be the correct solution. So, and again, a lot of people were getting this correct, right? Some people even wrote, right? Not only columns, but some people were literally saying, oh, this is actually, there's no rotation because this is the kinematic chain, or yeah, they were basically explaining like, oh, L2 doesn't need to rotate with respect to its parent, blah, blah, blah. But they had, the column 4, they had a problem, right? So some people, for example, give us 0, 0, 0, right? Either with 0 or 1 in the last column, right? So that was also another mistake. But a lot of people, for example, were thinking something like this, saying, oh, there's no rotation, so there's also no translation. Well, that was wrong because there is translation also if you're thinking in local coordinates. What? Right? So this should be one possible solution, right? So basically we had several possible solutions, right? So this is one possible solution and it's perfectly fine. This is another possible solution. And again, if we were seeing that your third column, right, which is basically the vertical one, your third column was pointing into the right direction, and maybe, I don't know, if you had, for example, let's imagine that someone had a -1 here, right? We were still giving points for that solution, right? Because yeah, at the end it's just like a flipping and it's not a big deal. And also someone could think that everything is not like that the local coordinates from the links is the vertical axis is not the z value but the y value, right? So it means that everything will need to change, right? The column needs to change because now you need to assume that the one that is pointing to the end effector is not the third column but the second column. And again, if you were answering the questions like that, we were giving full marks if it was correct, if everything was correct, assuming that it was the y value, right? So basically, after this explanation, if you still think that maybe there's a problem in the grading, of course, we are always open to discuss that. So you can obviously send us an email. So this is basically the explanation. So I will stop the video here and then I will make another video now explaining the solution for the transformation bonus part.